Okay, hello everybody. Welcome to the GCSE and A-Level Physics revision session I'm doing tonight. It is the 23rd of April 2024. The first session, as I'm sure lots of you are familiar with, is going to be all about GCSE physics, and I've got some questions here we're going to be going through, looking at various things including radiation, and then later on there's going to be a question a little bit later in the live stream about the density of a small rock and the kind of experimental methods. So this is really good preparation for anybody who's got their GCSE exams coming up for both paper 1 and paper 2. If you are in the chat, if you've subscribed to me on YouTube, then I can see the live chat as we're going on. And of course, if you are watching this afterwards, so maybe you've come back to this and found it either through YouTube or my GCSE or A-Level website, then obviously you can see the kind of the random stuff that goes in the chat, and of course you can catch up with any of the other live streams I've done. So hello to some people I've seen before. Joe Smith, hi there. Katzoi, hello as well. So yes, shall we just begin with some physics? So the first question is about the demonstration of a radioactive source. Oh yeah, everybody's joined now. Joshua, Chop, Free Maths Lessons, Joe Smith. Somebody's seen the video of me on Uplearn. Yes, for those of you doing A-Level Physics, Uplearn have used some of my videos. So for a lot of people, I am the voice of Physics Uplearn. And yeah, of course, you can find everything from there over on my own website, either on GCSE Physics Online or A-Level Physics Online as well. Okay, so the topic, the first one we're going to be looking at is, I guess, partly to do with the experimental method, and this one here in particular is looking at the count rate of a radioactive source. So this is what is measured by a Geiger counter. So they've got a Geiger counter, and what they do is they change the distance that the detector is away from the source. So basically imagine this is a radioactive source. They put the Geiger counter a certain distance away, they look at whatever the count rate is, and then they move it to a different distance and look at how that amount of radiation depends upon the distance from the source. Okay, so the teacher tells the students that the count rate is inversely proportional to the distance from the source squared. Explain if the teacher is correct. Now, I would say that this is a very, very difficult GCSE style question. If anybody out there is an A-level student, then you'll realise that what we have here is like this 1 over r squared relationship, which is something you might investigate in year 13 looking at gamma. So yeah, use data from the table and the graph in your answer. So the important thing that I think is kind of key here is that we need to use some data from the table and also potentially from the graph in your answer. So it's not just good enough sort of stating a sentence, you need to quote some numbers. So if we're talking about data, that means we need to quote numbers. Okay, is the teacher correct first of all? Well, let's have a look at what happens, okay? So let's have a look at a distance, and we could pick any one of these, but let's have a look at maybe 5 centimetres. When you've got a distance of 5 centimetres, I'm just going to go up the graph here, and I'm going to go across. Okay, and what we can see is when the distance is 5 centimetres, the count rate is equal to about 25.5. Okay, it actually says it in the table here, but there we've got a number of about 25,500, because here we've, is that right? Oh, have I made a mistake? Oh no, there's a mistake in the paper. Oh God, I'm actually gutted about that. Count rate times 10 to the 2. That should be times 10 to the 3. So I'm going to have to go and make a correction to all of my exam papers I put out there. Okay, let me just circle out, and that'll be something I'll do later. So we've got the count rate here. If we double the distance from 5 to 10, so I'm going to do some other lines up here, and this one goes across to there. What we can see is when we go from 5 centimetres up to about 10 centimetres, the answer is about 6.4, okay? And it says it in the table here, so that's about 6,400. Okay, So what we've done here is we have doubled the distance. So that's gone up by a factor of 2 because we've gone from 5 to 10. Now the other number, it's gone from 25,000. It's gone from 25,500 down to about 6,400, and therefore it's gone down by a factor of 4. Okay, and of course we could take any 2 points in this. So we could go from maybe 6 to 12, we could go from 8 to 16, and what we find is as we double the distance, the count rate goes down by a factor of 4. Okay, so yeah, as Free Maths Lesson says in the chat, as distance increases, the count rate decreases. But if you double this, that goes down by a factor of 4. So effectively what we're saying here is that, let's say D is, or we could maybe look at the count rate. So I'm going to call that C to be, or I'm going to call it CR to be the count rate. That's proportional to 1 over D squared. Okay, so the count rate is proportional to 1 over D squared, because if you were to double the distance, this number goes down by a factor of 4. Okay, use data from the table and the graph in your answer. So first of all, we could say that, explain if the teacher is correct. So the first thing I'm going to do is say that they, the teacher, are correct. If you double the distance, the count rate goes down by a factor of 4. And of course we needed to use data in that, and therefore do we need to know that proportional equations thingy for maths lessons? I'll come on to that afterwards. Yeah, if you double the distance, the count rate goes down by a factor of 4. For example, as you double from 5 centimeters to 10 centimeters, the count rate drops by 4 from 25,500 to about 6,400. Okay, so as part of this answer, we've got the fact that they're correct. We've kind of stated that that happens, and then we've got some numbers, and that's kind of the thing that gets you the mark. Now, for GCSE, there tend to be 2 things that you need to be aware of. Okay, so if I just turn this over. So what you need to look at is 2 big relationships. Now, the first relationship, say you've got A and B, and we've got some data that looks like this. And here we have the origin. If you have a straight line, and it goes through the origin, then we can say that A is directly proportional to B. Okay, and this symbol here just means proportional. That's the first one. The other type of data that we might have sometimes is maybe we had C and D, and what we see is a relationship a bit like this. Effectively, as D gets bigger, C gets smaller. And if you were to plot that data maybe like this, where we maybe plotted 1 over C against D, we then get, again, a straight line. So it's a straight line. And it goes through the origin. And here we can say that D is proportional to 1 over C, or you could say that C is proportional to 1 over D. And here we have 2 things which are inversely proportional. I would say that these are the 2 things you need to know about. We've got things which are directly proportional, and we have things which are inversely proportional. This question, though, was a little bit more tricky because it wasn't just inversely proportional. The count rate was inversely proportional to D squared. So that one was a little bit more tricky. Okay, let's go on to another question. The teacher brings the radioactive source to a distance of 10 centimeters from the counter and places a piece of thick lead in between the source of radiation and the counter. Explain why the count rate does not drop to 0. Okay, Chop ATR says, in physics, can we use the equation that C equals K over D? Yeah, we can also say that in this one over here, if C is proportional to 1 over D, then C is equal to K over D, where K is just some constant of proportionality. Just like up here, we could say that A is equal to KB. Okay, and if you've done it in GCSE maths, the people marking your papers, they will understand it. So, going on back to this question, why does the count rate not drop to 0? So basically, even if we block out all of the radiation from that radioactive source by using a thick piece of lead, that's going to block out the alpha, it's going to block out the beta, and also it's going to block out pretty much all of the gamma. The things you could say is that it's due to background radiation. And that could be coming from outer space, it could be coming from rocks underground, it could be just due to some radioactive gas in the air. The other thing is that another option that you could have, or you could say that the gamma doesn't stop all, sorry, the lead doesn't stop all the gamma. Because even if you have a thick piece of lead, some of the gamma radiation is going to be getting through it. So either of these would be an absolutely fine answer. Okay, for 9.3, we then have these tongs, and if this is something that you've seen in your school, you should have seen your teachers demonstrating different sorts of radioactive materials, looking at alpha, beta and gamma. I've got a video, of course, on my website where I show that as well. So what we have is this really long pair of tongs. Okay, and here we have the radioactive source at the end. And really, the reason we do this is to reduce the risk of irradiation. Okay, so the question then is about defining the term irradiation. Okay, so this is something you need to know about. And you need to be very clear about the difference between irradiation, which is being exposed to radioactive materials, and contamination, which is actually when you have that radioactive material upon you. So irradiation is exposure to radiation from a source. So if you imagine holding onto these tongs, when you're holding onto them, there's going to be radiation being emitted from this. So there might be some alpha, there might be some beta or some gamma going in all directions. Now, the further you are away from it, the less of that radiation is going to reach you. But as soon as you put this back in the box, you're not being exposed to any more radiation. Even if some alpha, beta and gamma have actually hit your hand, once you've taken this away, those alpha, beta and gamma will have disappeared. They'll have been absorbed by other things. So, exposure to nuclear radiation, as Anissa says, exposure does not mean directly touching the source. So what you're doing here is you're not touching the source, so you're not going to be contaminated. So basically you might be irradiated by the source, but there's none of the particles of that source kind of actually leaving this and actually getting onto your fingers, okay? If you've got bits of the radioactive source here, and then it ends up, some of these bits of dust, or small bits of that stuff, if they stay on your hand, you are now contaminated, and again, you are now being continually irradiated by this radioactive material. Okay, hope that's good. Right, the source is stored in a lead-lined box when not in use. The half-life is 148 days. They measure the current activity as 30,000 becquerels. If the source is 2 years old, calculate the initial activity of the source of radiation when it was first placed in the box. So for a question like this, looking at half-lives and activity, I think what you need to do is just think about, first of all, how many half-lives of 148 days are they going to be in 2 years? So 2 years is equal to 2 times 365 days. So if I just work that out, that's 2 times 365 is 730 days. Okay, and to work out the total number of half-lives, the number of half-lives is going to be equal to 730 days divided by 146 days per half-life. And as if by magic, that's exactly equal to 5 half-lives. Okay, now of course, if we've got an activity after 2 years of 30,000 becquerels after 2 years, that's the same as after 5 half-lives. So what we need to do then is we need to multiply this by 2, by 2, by 2, by 2, and by 2. Okay, and that will tell us the initial activity, which must have been much higher, but it's dropped by a half and a half and a half and a half and a half over 5 half-lives. So effectively what we need to do is we need to multiply 30,000 by 2 raised to the power of 5, which is equal to 960,000. So I reckon the initial activity was 960,000, and that's halved 5 times. So a question like this, there's not really one exact formula. You can just plug your numbers into at GCSE, but it's more of like a sort of logical kind of thing that you can go through. Okay, right. The next question then is about a different radioisotope, and the word radioisotope just means a radioactive type of element. Okay, it's a short half-life. It's called barium-137. It decays by gamma emission to become more stable. What happens to its nucleus when a gamma ray is emitted? So, to be honest, for this question here, the fact it's got a short half-life is irrelevant. The fact it's barium, or barium, is kind of irrelevant. But what we need to know is that it's being becoming more stable by emitting gamma. So, what we could say is that there is no change to the structure of the nucleus in terms of the number of protons and neutrons. And the reason for that, and I think this is really the important thing to get that second mark, is to explain that gamma is a wave of energy, not a particle. So when gamma is emitted, all that's happening is from the excess energy in that kind of highly energized, the nucleus is in a high energy state, it just emits a little packet of electromagnetic radiation, and by giving out some energy, it drops down to like a lower energy level and becomes more stable. Okay, yeah, there we go. Why did I do 2 to the 5? Or, yeah, so basically, for this one over here, we know the activity after 2 years, but we want to know the activity 2 years ago. Now, 2 years is the same as 5 half-lives, which means in that time, the activity is halved and halved and halved and halved and halved. Now, if we wanted to know the activity 1 half-life ago, we'd double it. If we wanted to know it 2 half-lives ago, we'd double it and double it again, which is kind of 2 squared. The activity 3 half-lives ago would be double it, double it, double it, so 2 to the power of 3. So going back 5 half-lives, this is the same as 30,000 times 2 to the 5. Okay, hopefully that's making sense so far. So we've done some questions there about radiation. The next questions are about a different method of measuring the density of a small rock. Now, yesterday, or a couple of days ago, I looked at an approach where we had a cube, so this regular shape that you can make the measurements of. This one here, though, is about the density of a small rock. So just have a quick read of the question. And of course, if you want to download your own set of questions, then you can go to my shop. I've got a new shop on Shopify. It took me a while to set up. It's physicsonline.shop, which I think is a pretty cool URL. If you go there, you can buy 12 of these practice papers. I've got 6 papers for paper 1, 6 papers for paper 2, and I guarantee if you have a go at these as part of your revision, you will get a better grade in your exams. Okay, so Abdul, yeah, this is the water displacement method. So we've got a small rock, and therefore this is going to be an irregular shape. Right, the first question though, although there's lots of information, I think this is a tricky thing. It's not just about doing some sums, it's about reading lots of information, and then you have a question where you need to try and work out what's relevant. So the mass of the rock is 37.8 grams, and we want to know the resolution of the balance used to measure the mass of the rock. So I guess often we call these the weighing scales, but basically a balance or a mass balance is used to measure the mass of it. And I would say because we can measure to the nearest 0.1 of a gram, I would say that the resolution is 0.1 grams. Okay, so you need to have the number to talk about it, and also we need to have the unit of grams. And that's basically saying that we can measure the nearest 0.1 of a gram, which is pretty accurate. The next thing we're going to do is we're going to calculate the density of the rock with appropriate units. Now, I would say the appropriate units could be grams per cubic centimetre, or they could be kilograms per cubic metre. Now, both of these, Hookian, hello, how are you doing? Sometimes they say precision. Yes, they do. This is the thing. Some exam boards have a slightly different terminology. But yeah, how precise something is really kind of tells us, I guess, effectively how close we can measure to. And we can basically measure to the nearest 0.1 of a gram with this instrument here. Yeah, it's like the lowest decimal point that you can get. Okay. Yeah, and I think people have said like CHOP and Thruxy, yeah, the numbers go up by 0.1 each time. So the resolution, the precision is 0.1 of a gram. Okay. Now, appropriate units could be grams per cubic centimetre. Ideally, you'd want to give everything in SI units of kilograms per cubic metre. So we're going to do both of these. Okay, so the density, first of all, we know that the density is equal to the mass divided by the volume. Now, the mass up here is equal to 37.8 grams. And the volume is 14.1 centimetres cubed. So if we were to just give our answer in grams per cubic centimetre, we just divide the two things together, which is equal to 2.68 grams per cubic centimetre. And that answer there is fine. Okay, Anissa, I think, has got the right thing. Cool. Now, somebody says, Caitlin says, you always put cubed per gram instead of it being the right way around. Why does it matter to have the right way around? I guess because the density is just the amount of stuff in a given volume. And that's because it's the amount of stuff in grams or kilograms in a volume, centimetres cubed or metres cubed. That's what we mean by density. So it has to be that. Okay. Now, the other way, which I think is better, personally, as a kind of pure kind of physics teacher, is we want to give stuff in these units. I'm going to show you how to do that as well. So the first thing is we need to convert each of these into SI units. So again, the density is equal to mass divided by the volume. Now, if it's 37.8 grams, that's 37.8 times 10 to the minus 3, if we were to give that in kilograms. Okay, that's the easy bit. The difficult bit is converting from centimetres cubed into metres cubed. Now, effectively, a centimetre cubed is a centimetre times a centimetre times a centimetre. Now, if we think about what that is in metres, that's basically 10 to the minus 2 metres times 10 to the minus 2 metres times 10 to the minus 2 metres. Now, of course, I'm sure a lot of you get this. We've got 10 to the minus 2 times 10 to the minus 2 times 10 to the minus 2. That's the same as times 10 to the minus 6 metres cubed. So 1 centimetre cubed is equal to 10 to the minus 6 metres cubed. That makes sense? So yeah, as people have said, I think divide by a million. Joe Smith, yeah, completely correct. So I would say that if we want to think about this volume, it's 14.1 cubic centimetres, but that's going to be 14.1 times 10 to the minus 6 metres cubed. Okay, now, I think the best way to do this is in one step in your calculator. So you do need to be confident with your calculator and start using today for all of your revision the calculator you're going to be using in your exams. Don't use your mobile phone. It's a different kind of way of calculating things. Use the calculator you're going to use in your phone. So use the calculator that you're going to be using in your final exam. So we've got 37.8 times 10 to the minus 3, close brackets, divided by open brackets, 14.1 times 10 to the minus 6. And this gives a number, equal to 2680 kilograms per cubic meter. Okay, so the density we could say is 2,680 units of kilograms per cubic meter. So I would say people getting adverts from YouTube, yeah, I'm afraid that YouTube just does that. But, you know, keeps me paid. I don't know if, actually, I don't know how much money I've earned from the previous live streams. I suspect it's probably about £1.50 in total. Now, the reason I changed it to kilograms of cubic meters is because I think that this is a more appropriate unit. And I suspect that if they give you a question like this, where they give you masses in grams and volumes in cubic centimeters, they're going to give you a lot of marks to do this. And I think this is a really kind of high level question of that converting of units. But I reckon at GCSE, if they just say appropriate units, grams per cubic centimeters are fine. But they might say to give something in kilograms per cubic meter, in which case you need to understand how to convert from centimeters cubed into meters cubed. Okay, the next question is, state and explain the effect that the following errors would have on a student's calculated value of the density compared to the actual value. So I'm just going to write down that density is equal to mass over volume. Okay, now if the volume of the rock is measured first, and then its mass is measured while the rock is wet, what's the effect going to be? Well, let's think about what happens, okay? So if we measure the volume of the rock first, then we know that the volume of the rock is correct, okay? If we measure its mass when it's wet, then the value of m is going to be equal to a value which is too high, okay? So if the mass is too big, and we know that density equals mass over volume, we could say that effectively the density, because the volume is correct, the density is going to be too high. And this is because the mass measured is too high. Okay, so what we can say is, by looking at this equation here, if we've got the correct volume but the mass is too big, this means that the density is going to be too big. So yeah, so this would increase the value of the volume. Now, if some water splashes out of the measuring cylinder when the rock is dropped in, and for this approach here, what they did, they didn't use a Eureka can. What they did was they basically had a measuring cylinder that had some water in it. They then dropped the rock into the bottom. It's going to sink down to the bottom there. So that's our rock at the very bottom. And that's going to mean that the reading on here goes up by a certain amount. And the increase in volume is going to be equal to the volume of that rock. So this is a way that you can actually measure the volume if you've got the right size kind of thing that you're measuring without using a Eureka can. Now, if some of the water splashes out when the rock is dropped in, the effect is that the volume is going to be too small. Okay, so we might have the correct mass of rock, but the volume is too small. And if the volume is too small, this is also going to increase the density. Okay, because we can see here how the density is inversely proportional to the volume. So if the V is too small, then density is too high. Okay, so basically here the density is too high is the effect. The explanation, I should have really put down here, is that the volume measured is too small. So we're going to get, again, as Abdul said, a higher density. Okay, we then have the final part. We've got 2 minutes left. Let me just get a quick swig of coffee. So just again, have a quick read of the question here before I answer it. So this time they used an irregular solid. It's less dense than water. Now, basically all they did in the method on the previous bit here was they basically just placed the rock into the measuring cylinder and they measured the volume. Now, the thing is then, so imagine we've got the same kind of thing. We've put our irregular thing in, but its density is less than water. It's going to float like this, okay? And that means the volume that we actually measure is only equal to the volume of this irregular solid that's underwater. Now, what you need to do is, if you do measure an irregular solid, which is less dense than water, what you need to do is basically push it down so the total volume of water displaced is equal to the total volume of that. And a way to do that could be that you basically push it down with like a piece of wire or a paper clip or something small like that. So you're basically pushing it underwater. You don't need to apply a force. And that means the value of V would be too low. So the density would be too high. And basically that's the answer. So let me just check if I've written down everything. Of course, if you do want to buy a set of these papers, they do all come with a full set of work solutions that look exactly like this. I think my handwriting is fairly consistent from one to the other. So yeah, the object would float in the water. So the measured volume of water displaced is not equal to the volume of the object. This means the density would not be correct. Yeah. Another person says, so Joe says, okay, right, so we've got some good comments here. We've got a lot of science is just common sense. Yes, I completely agree. By just thinking about this in a logical manner, you can get a lot of marks. You could basically go into an exam. I reckon you could go into a GCSE exam with no physics knowledge, but just a lot of common sense and get a lot of marks. If it floats, you could use a different fluid like oil, maybe to get the actual volume displaced. Although I'd have thought if it floats in water, it's going to float in oil as well. We need to make sure it's just that thing is actually pushed all the way underneath it. Darren, this is now a question about A-level. Do I sell AQA A-level papers? Yeah, so I've got practice papers for paper 3A for AQA A-level. These, I've got 3 of them, alpha, beta and gamma, and you can find all of those on my shop, which is physicsonline.shop. You can buy them tonight. They will be delivered to you by email tonight, and you can start working on them tonight as well. Okay, so I think that will kind of conclude our GCSE stream. Thank you so much, everybody. I will be back tomorrow. If you want to find out what I'm doing, then just head over to gcsephysicsonline.com/live. There's all of the resources that you can download immediately. It's all digital stuff that you can like work through these questions, and you can see the topics I'm going to be doing to help you revise over the next few weeks and get ready for paper 1 and paper 2. Right, now we're going to go on to the A-level stuff. So goodbye to the GCSE crowd. Hello to the A-level lot. Tonight, I can't remember what I said we're doing. Oh yes, tonight we're going to be doing some stuff about different sorts of lines of best fit, which I think is important. And also we're going to be looking at G by freefall, which is a really important thing. And of course, these questions, they came from my daily workout book 3, which basically revises pretty much everything that you've already covered in year 12. So if you want to get the good marks, you want to kind of prepare for your exams and either real AS exams or maybe mocks that you have in school that inform your UCAS grades, it's worth getting this book, and it will revise pretty much everything of the core content you've done in year 12. Okay, so let's begin by drawing in a line of best fit for the following data. So I would say, as normal, pencil and a ruler. I think the first one here looks like a straight line, and we want to get approximately the same number of points above it and below it. So I reckon, oh, this is tricky, maybe something a bit like that. Okay, so the first one, that's okay, I suppose. The second one, I reckon we have an anomaly. So I'm just going to identify the anomaly. Radiating radiator. I saved you in your mock yesterday. Oh, that's so good to hear. I hope you did all right, and I hope that some of the stuff I've done has kind of helped you through your A-levels. But yeah, I hope it's all going all right. Okay, the next one, I reckon we've got, like, again, like a straight line. It doesn't seem to go down to the origin, so I'm just going to put in a straight line like that. And we've identified the anomaly and like not used that. Okay, the next one. This is where sometimes not having many data points doesn't help. I know this one does have. It's got a point at the origin down here. So we can't force a straight line through that. And don't forget, of course, that the line of best fit can be a curved line as well as a straight line. Does the line of best fit always have to touch the y-axis, or is it okay not to touch it? I reckon, like Arjun, that you don't have to always go back to the y-axis, but I reckon there's no harm in it. And I think, especially in A-level physics exam questions, the reason that they want you to draw in a line of best fit, if they do that, is because the gradient will be used for something and the y-intercept could be used for something as well. So I reckon if you've got the option, just make it go all the way to the y-intercept, and then it means you're not going to sort of leave that line too short. Are we going to do anything related to absolute uncertainty? Let's have a look. Are we going to do some absolute uncertainty stuff? We will, potentially. Maybe not lots of it, but a little bit, Decky. Okay, right. Okay, so this one over here, we've got a curved line, and it looks a bit like that. And this one here, we can see we've got a curved line. So again, I'm just going to move the paper. That's really important. And I'm just going to commit to it in one straight line. So we get something that looks a bit like that. Okay. Now again, the things that you don't want to be doing is you don't want to be doing like a sort of a wiggly line that you do too slowly. And if you do it too slowly, it ends up looking like this, which is absolutely rubbish. Equally, you're not in arts. You're not kind of sort of sketching a line. Stuff like that isn't good either. And I would suggest that you do it in pencil in your exam. So if you make a mistake, you can just rub it out. And then maybe towards the end, if you know that you've got the right shape, you can go over in your pen to make sure it's scanned in. Right. 78J. Will I continue to do more A-level live streams after the 28th of April? Of course I will. I just haven't put them up on my website yet. I think that's all I've done so far, although today I've planned out what I'm doing for the next few weeks. Okay, so there we go. Got some nice curves there. So that one there, just a few lines best fit. Now, I'm going to call this, I just like this, the line of best fit. I'm going to call this the lob off, LOBF. And also what we have is our worst acceptable line of best fit. So I'm going to call these the lob off and the lob off. Okay. So yeah, the first one, the line of best fit, we're going to ignore these error bars. Now I think error bars come up a bit more in AQA rather than OCR. So I reckon the first thing I'm going to do is just look at the crosses, and I'm going to put in a line of best fit like this. Okay, so that is my line of best fit. So if I just label that as LOBF, that's my line of best fit there. I'm just going to label that in green. Now, the worst acceptable line is a line that has to go through all of the error bars. Okay, so you can't have a worst acceptable line like this. You can't have a worst acceptable line like this. I mean, strictly speaking, if I did a line like that, we've got half the points above and half the points below the line, but it doesn't really work like that. So I reckon what we need to do is we're going to just line up the ruler. I'm going to do this one in red. I should probably use a pencil, but the red should hopefully make it clear. Okay, so that line in red is going to be my worst acceptable line of best fit. Okay, now it doesn't matter if you go steeper or shallower. It's just like some line, and there's no precedent. It doesn't have to be steeper or shallower. It's just a line that would go through, in this case, the error bars. Okay. Now, for some people in Edexcel, this might not be in your course, but it still might be relevant just to kind of understand, because if you've got your line of best fit and your worst acceptable line, you can use that to work out the uncertainty in your data. Okay, right, so let me just put a few people in timeout. Sorry about this. Okay, just going to time out some people in the chat. Right, the next one then is we've got this data here. Again, we've got like a fairly straightforward. I'm going to do this in green to make it clear. This is my line of best fit that goes through the data. Do you want to go steeper or shallower? So let me know in the chat. Steeper or shallower for my line of best fit. My worst acceptable line of best fit. Okay, so do you want to go steeper or shallower? Shallow, so smokes. Yeah, you're first in. Let's go shallower. So we could just have a line that basically goes through it a bit like this. Okay, so the line in red is the worst acceptable line of best fit. Steeper, shallow, steeper. Okay, we've got kind of a fairly mix. And yeah, what I'll do, Darren, is I'll talk a bit about uncertainties afterwards. Okay, so again, we've got another line over here. Fairly straightforward, and the idea with this book is just lots of practice. So we've got our line of best fit, and then we've got our worst line. I'm going to go steeper this time for all the steeper crowd. So Abdul, Light Arjun, the real Joe Linton. We're going to go steeper, so let's put it like this. I'm really looking at the first and the last one. And if we go steeper, it's a steeper magnitude of gradient, but it's more negative. And that's going to be my worst acceptable line of best fit. Now for this one, we can't really, if I put in my line of best fit, it's going to go through the data like this. Okay, now there's no line that goes through all of those error bars, and the reason for that is we have an anomalous result down here. So we're just going to ignore that like you would normally, and I'm just going to go for a worst acceptable line like this. So sometimes it's called the worst acceptable line, sometimes it's called the line of best fit. And the reason for that is we can actually look at the uncertainty in the data. What we can see here probably is that the two gradients here for C are fairly close. They're kind of like this and this. They're kind of like pretty close to each other. Whereas the two over here, the gradients are much more different. And therefore we're going to be less certain about this. And this is because there's an equation that basically looks at the uncertainty in a line of best fit. And what we can say is that the percentage uncertainty is equal to the value of the gradient of the line of best fit, take away the gradient m of the worst acceptable line of best fit, and that's divided by the gradient of the line of best fit. Now, it doesn't matter if the line is steeper or shallower, so we're just going to look at the modulus of this, the positive value, and then of course we multiply that by 100. Okay, so the real Joe Linton is the line of best fit from top to bottom. It's just basically through the middle of the error bars. Okay, so imagine that the error bars aren't there. Draw in a line of best fit through the data point, so you have like an approximate number above and below, and then the line of the worst acceptable line is the one that if you've got error bars, it goes through those, or if you've got like a wide spread of data, it's the worst line you could possibly fit there. Okay, so basically that's the way to look at calculating the percentage uncertainty in this data. Is that okay, or does that confuse people? I think for some people doing Edexcel, you tend not to use error bars. I think in AQA it's asked a little bit more often. Okay, something else I guess within my book is I do have information. So I think what date we're about the 12th of April. So within the book I do have things to help you kind of like structure your revision and things, which is kind of an important thing to do. Of course, if some of you have this book at the moment, the date in real life is the 23rd. So if you were doing this book, then today there'd be a question about critical angle. We're looking at the path of those rays of light. We've got something about step index, optical fibre with different sorts of glass. Then tomorrow, you'd be doing questions which are practicing sinusoidal curves. So like depending on the frequency and amplitude. So this is just kind of practice. And then the next day you'd be looking at some of the base units for these, some definitions, and a question about equilibrium and stuff. So yeah, this book here could be useful. So you can buy it on Amazon. Right, the next question then is about looking at G by freefall. So I would like to know in the chat, either yes or no, has anybody in school done the practical where you have a ball bearing held up by a magnet, you turn off the electrical supply, this drops down and it opens a trapdoor? Okay, so for all of you, yes or no, have you actually done this practical in school in year 12? Yes, says Panda Gaming. No, says Ben. Yes, says Tommy. Yes, says Darren. Oh my God, there's quite a lot of people. Joe Smith, sadly not. Moodle, Mip, yeah. Jacob, yes. Elegant, no. Shahad, no. The real Joe Linton, yes. Okay, so there's quite a mix. Done it, didn't work very well, says James. Yeah, that makes sense. Abdul, no. Only looked at this from a textbook, says Light Arjun. Big Trav, with a light gate. So a slightly different method, but the same principle. Josh P, yes. Jamie M, no. Selena, no. McRae God, no. Eva, yes. Cara, but with a sensor at the bottom. Light gate for Darren. Lunabot, no. And yes, says Johnny. So basically, for A-level physics, you just need to be aware of different methods of measuring the acceleration of freefall. Little g, the acceleration due to gravity. Now, this is one of the methods that some schools have the setup and it works really well. Some of them don't have it. GVK has seen it. But basically, you have an electromagnet here. And the electromagnet is attracting this ball bearing. Now, when you turn off the electricity for this, it starts a timer and the ball drops. So as soon as you turn off the electricity, it's no longer an electromagnet, it's just a bit of metal. The ball bearing is no longer attracted to it, and it falls down. The timer starts and the timer stops when a little trapdoor, or sometimes you have a sensor that kind of detects the impact, it times how far it drops, or how long it drops for. And the best way to do this is that you basically alter the height of this. You get some data and then you can plot a graph to use that to find G. So let's go through this kind of sort of step by step. So we've got the height it drops from. We've got the mean time in seconds. And the first thing we need to do is just complete the table. So this is a case of simply squaring this number. So this is basically like a year 5 student could do this. And also we're going to keep our data to 2 significant figures like this. So we've got 2 significant figures here. I'm going to give this data to 2 significant figures as well. So we've got 0.20, 0.27, and 0.32. Okay, so we've got some numbers there. This is an A-level practical, often carried out in year 12. But if you're in year 13, you still need to know about this, because don't forget that you will be assessed very soon on everything you did in year 12 as well as year 13. So if you're in year 13, you need to know about this. Okay, we're then going to basically just plot some data. So we're going to plot a graph of time squared against height. Do you need to know how to draw the circuit for the ball bearing apparatus? Josh, you don't need to know the circuit diagram for this, because often there's different circuits you could have set up. And it's more about the principles, the physics principles, rather than the detail of the circuit. Okay, so let's just plot that data. So we've got height along here. So when it's 0.3, it's 0.084, which is kind of like there. And then we've got 0.6, and it's 0.14, like that. And then a 0.9, and it's 0.2. We've got 1.2, 0.27, and then of course we've got 1.5 and 0.32. Okay, what would you know? Perfect straight line, pretty much. So let's see what happens. If we put this here, we get like quite a nice straight line, but it doesn't go through the origin. Okay, so I would say if we try to force this through the origin, then the data here doesn't really fit. So what I'm going to do is, for this, I'm going to do a line of best fit that looks a bit like this. Okay, that is the approach I've made. Okay, so plot a graph, calculate the gradient. Now, what do we do? All of you might have seen this last week. You might have seen some of the titles for some of these live streams. In order to work out the gradient, don't take shortcuts. Just go through the basics and draw a massive triangle. So I'm going to draw a massive triangle on here, and the triangle doesn't go up to my data points. It goes up to the line of best fit. So it's going to do something like this. Okay, so I've drawn a massive triangle. And then we're going to calculate the gradient. So the gradient m is equal to the change in y by the change in x, which is equal to about, I reckon it's about, let's just say 0.32 minus 0.02 divided by 1.5 minus 0. So that's equal to 0.3 over 1.5, which is equal to, this one is just in my head, So I would say that's equal to about 0.2, and that is not the final answer. Okay, so what would the units be for the gradient? Because again, this isn't maths, it's physics, we must have units. So what are the units for this gradient? So we've worked out the magnitude of it as 0.20, but what are the units looking at the graph that we have? And I think a lot of people are asking some good questions. Okay, we've got somebody saying, yeah, I think a few people have realised this. Because we've got time in seconds squared divided by height in metres, it's actually going to be seconds squared per metre. Okay, and then of course, as I think Cara, Johnny, Tommy, Joe and Light have said, and I know a few people have retracted their comments, this is basically going to be related to the metres per second squared, but it's like the reciprocal of it. So yeah, use a gradient to determine the value of g, the acceleration of freefall. So this is why we do it. The whole point in taking not just one reading, but a whole series of readings allows us to work out the gradient. And that means if you had maybe a bit of data that wasn't quite correct, you could tell that that wasn't fitting the pattern. You could discard that data as an anomaly, and this is going to give us a much better value of g. Okay, now let me just explain this. So let's just go back to looking at SUVAT. Okay, so S, U, V, A and T. So because we've got a motion problem, we're going to ignore air resistance because it's only going relatively slowly. The distance it falls is going to be equal to the height. It starts at rest because initially that ball bearing is kind of at rest on that electromagnet. We don't know the final velocity, but we know the acceleration is due to the acceleration due to gravity, and we know that the time is something that we've measured. Okay, so what we want to do is have a SUVAT equation that doesn't have a v term in it, and we can therefore say that S is equal to ut plus a half at squared. But of course, using the things that we have down here, the distance it falls is h, ut goes to 0, and h is equal to a half times at squared, which is gt squared. Okay, so this is the equation that we can use. Does that make sense so far? So we know that the height dropped is equal to a half gt squared. I'm just going to write that down over here. So the height it falls is equal to a half gt squared. Now, we worked out the gradient previously as a time squared over h. So we can also say that the gradient, I'm just going to call it m, is equal to t squared over h. And if we rearrange this, we could say that 2 over g is equal to t squared over h. So all I did was I brought the h down here, and the half g comes up to be 2 divided by g. So 2 over g is equal to t squared over h, and therefore the gradient that we calculated is equal to 2 over g, or we could say that g is equal to 2 divided by the gradient. And that's where we have this half term, so it's not just reciprocal. And therefore, this is going to be equal to 2 divided by the gradient, which is 0.2. And if you do 2 divided by that, I don't need my calculator, this is equal to about 10. And the units, because we've got a number over second squared metre to the minus 1, is going to be metres per second squared. Okay, now, how do I know to use SUVAT? Emma, that's a really, really good question. I think it comes from basically just doing lots and lots of questions. Okay, we still have basically an object which is falling under gravity. We know the height it falls is h, so we know that distance it falls. We want to work out the acceleration, and we're measuring t. So if we were to be given a question like this, you think, well, okay, SUVAT, that's going to solve it. But also, we can still apply SUVAT to these kind of sort of practical things as well. Okay, so we can use SUVAT because we're going to assume there's a constant acceleration because the effects of air resistance are negligible at these relatively low velocities. Now, the last bit is suggest a reason why the line on the graph does not pass through the origin. So I'm going to let some of you out there maybe think about why that is. Why is it that the data doesn't go through the origin if we had real world data? So why is it that as soon as you press go on the timer, there's some issue with the timing between the ball dropping from here and hitting that? So Chanruni says systematic error. Yeah, so basically friction, reaction time, I would say when we talk about reaction time, okay, so I reckon if you say human reaction time, that's not correct because it says over here, pressing the switch starts a digital timer, which opens a second circuit which stops the clock. So really it's not a human starting and stopping, it's the electrical circuit which does that. Moodle MIP, is that how you say your name? Moodle MIP. Yeah, this is a good point. Sometimes when you turn off the electromagnet, it still has a residual magnetic field for a short amount of time. This should be made out of magnetically soft iron, but sometimes when you turn off the circuit, this stays magnetic for a short amount of time, and that will then lead on to a systematic error. So it could be, and I'm just going to put down systematic error first of all. So we have a systematic error where basically every time we do something, a small amount of time has been added onto all of our readings. Okay, so there's some fault in the timing. And effectively, this is why the whole graph is shifted upwards. We have a systematic error in the timing. It could be potentially due to human reaction time, but in this case the circuit should kind of stop that. There could be a delay on the sensor, as Josh P said. Moodle MIP said that the electromagnet is still magnetic. Yeah, it could have a systematic error due to the timer having a delay when starting or stopping. So it could be a timing error within that electrical circuit. Would you get a mark for just saying systematic error? Yes, I think you would. But I think to be sure, it's always good to talk about a systematic error due to something, especially if you're asked to explain the source of the error. Am I the voice of the Physics Uplearn course? Yeah, Mr. Dan, I am. Yeah, Guy from Uplearn, the kind of guy behind it. I met him years ago, nice guy, and we've always got on really well. So yeah, I let them use a lot of my videos to help support their Uplearn course. They do pay me a small commission. But of course, if you want to keep supporting the work I'm doing, then head over to my shop, which is Physics Online. Actually, I'm going to write it in here. So if you go to my new website, Physics Online shop, does that take you anywhere? That will take you to my Shopify shop. AQA A-level students, go and buy my practice papers for 3A. Buy them today while they're kind of still useful to you, and that means they'll help you prepare for your 3A exams quite soon. Would air resistance mean that it isn't accelerated by only gravity, but the acceleration is lower? Johnny, if there was air resistance in this, then it would still be accelerated by gravity, but there'd also be a drag force. So the acceleration, because of the drag force acting in the opposite direction, so imagine we still had the weight acting down, there'd still be a small drag force d, and that means the acceleration would be less than the acceleration due to gravity. Right. So, do I have a cheeky discount code? No, I don't actually at the moment, I don't. Right. Would g not be 1 over gradient, because that would give metre second to the -2? Joel, it would give something, but because we've got this equation here, based on this Suvat equation about the height is equal to half gt squared, if you just did 1 over the gradient, you'd get a value of 5, which would be half the value. So the reason that we basically have to do 2 divided by the gradient to get our value of g is coming from this Suvat equation. Okay. Can +4 or +5 scale be a sensible scale? I think it depends. I reckon, again, if you're being assessed on this in the exam, they will give you plenty of graph paper for the data that they have. So I reckon going up in 1, 2 or 5 is best. Okay. Right, some good questions here from B about the Netherlands and if I should do some physics exams from the Netherlands. That is a good thing. I know lots of Indian students want me to do that. I had a really nice exam paper sent to me from Sri Lanka, and that looked really good, actually, really interesting. But at some point, probably once I've done a bit more of the stuff to support students in the UK and the international GCSEs, I'd love to do some more physics questions from around the world. So that's definitely something I will do. Right, I think we've come to the end of it today. Of course, don't forget, if you weren't in the stream yesterday, I do have this derivations book. You can find this on my website. If you go to the stream yesterday from the 22nd, there's links all over the place. You can basically download this completely free guide with lots of A-level derivations in it. And I think this could be really useful if you're in year 10. No, maybe in year 10. If you're in year 12 or year 13, this could be really useful to you. But basically, that is the end of the stream tonight. Thank you so much, and I will see all of you again tomorrow.